guys, this is Professor Janacek. I want to talk about an integration technique called integration by parts. Now, I'm not going to go over how this was developed, but it basically is a formula that we're going to use in order to integrate. If we have something that looks like the integral of u dv, then the result is u times v minus the integral of u of v du. One thing to notice on this is that our integral looks like it's in terms of one thing, but the differential is actually in terms of another. The key to this is going to be choosing our u value. I like to use a little technique called LIPET. Now, this is a technique that will help us with choosing u. It's not going to always guarantee that we have the right u or even the best u, but if you have no idea how to start choosing your u, I think it's a nice starting place. And it does often work. LIPET is just a little acronym to help us remember the order of the types of functions we'll be looking for. So the L stands for logarithmic. The I is inverse functions, like inverse trigonometric functions. The P is for polynomial. The E is for exponential. And finally, the T is for trigonometric. And this is the order that I look for in my integrand, and I'll choose u to be one of those in that order. I look for logarithmic before I look for inverse. I look for inverse before I look for polynomial. You'll notice that the trigonometric is kind of the last thing we look for. So let's take a look at an example. Let's start with the integral of x e to the x dx. Now, you'll notice that this looks like it's a product of two different things, and one of them is not the differential of the other. So in this case, I'm going to first look for a logarithmic function, and then there's no logarithms here, so not going to have that one. So next, try inverse. Again, no inverse functions, but I do have a polynomial function, and that's what I'm going to let u equal. And so in this case, we will let u equal to x, and then dv, notice back up here, u and dv is what I'm starting with. dv will be the rest of it. So everything else after that integral, so that's e to the x dx. If that's the case, then du is dx, that's easy enough, and v comes from the integral of dv, right? Integral of dv is v. And so in this case, dv is e to the x dx, so we're going to integrate e to the x dx, which gives us just e to the x. Yes, there's a plus c, but I'm not going to worry about that till the very end. Since this is an indefinite integral, I will have that arbitrary constant out there, but I don't need it over here on the side. So looking at this, we have this part is the u. This bit, e to the x dx, that's the dv, so that's exactly what I have up here in my formula. And so now all I have to do is write out the other side. Just fill in the blanks, if you will. That's going to give us u times v minus the integral of v du. So I'm going to start with u times v minus the integral of v du. So u is x times v is e to the x minus the integral of v, which is e to the x, du, which in this case is just dx. And now we simplify the last integral. We're going to just work with this integral here at the end. We have x e to the x, don't need those parentheses anymore, minus the integral of e to the x is e to the x. Of course, we now have our arbitrary constant. Again, I didn't need to write that in the work before, but I do need that now. And there you go. Simplify if possible, although this one doesn't simplify at all. Let's take a look at the second example here. We're going to integrate x squared e to the x dx. Again, going through the list, I don't have anything logarithmic, I don't have anything inverse, but I do have a polynomial function, and that's where I'm going to start with my u value. So we'll let u equal x squared, and that means dv is the remainder e to the x dx. And now let's see if we can figure out the rest of this stuff. If u is x squared, then du is 2x dx. And dv is e to the x dx, so v, being the integral of dv, is the integral of e to the x dx, which we know is simply e to the x. Again, I don't need that arbitrary constant over here in this side work. I will need that, though, in my final answer. All right, so using the formula, I'm not going to write it down this time. Hopefully you can see we're going to start with u times v, and then we'll take v du. So u x squared times v e to the x minus the integral of v, which is e to the x, times du, which is 2x dx. All right, we can simplify this just a bit. This is x squared e to the x. That looks good. Minus, I'll go ahead and factor that 2 out. 2 times the integral. You know what? Let me go ahead and put that x in front as well. X e to the x dx. Take a moment. Make sure you recognize what all happened there. It's just moving a few things around. And let's see. Now what? Well, this is not something that I can integrate easily. I can't integrate x e to the x. In fact, if you look back at example 1, it might look familiar. So it looks like I have to use integration by parts yet again. Because I'm going to do that, I'm going to go back and put ones on all of the u's and v's here so I don't get them confused here in a bit. So those are all u1s, v1s, du1s, dv1s. And so now let's go ahead and let u2 again be my polynomial part, which is x, and dv2 be what's remaining, e to the x dx. Again, you'll notice part of this becomes u, and everything else, including the dx, becomes part of dv. And if that's the case, then du2 is simply dx. That was an easy one. And v2 would be the integral of dv2, which is the integral of e to the x dx, which we know is simply e to the x. These are great functions to work with. Again, I don't need that arbitrary constant at the end. I'll just collect all the arbitrary constants at the final and the final answer and put them as a plus c. All right, so using our formula once again. So in this case, I already have x squared e to the x. That doesn't change. Minus 2, going to keep that out there. Now, everything after this integral, I'm using the formula again. So I'm going to use this u times v minus that integral. So we have, again, u2 times v2 minus the integral of v2 times du2. So we have x times e to the x minus the integral of e to the x dx. Notice all of that is going to be multiplied by -2 here in a second. Let's go ahead and simplify a few things. Still have all of this here in front. X e to the x, don't need parentheses on that, but this integral of e to the x dx, we can work that out. That is simply e to the x. Now, yes, I could say this is plus c, but I'm going to distribute that 2 out, and it's going to be a constant times 2. I don't really need that constant until after the parentheses. Again, a constant times 2 is still just a constant, so I'm just going to call it c rather than introducing all these c1s and c2s. Distribute that -2. Be careful, that 2 is negative, so it's going to be my x squared e to the x minus 2x e to the x plus 2e to the x. Watch that negative on there. And then we have our arbitrary constant there at the end. And ta-da, that's it. We're done. Enjoy.